Today we're going to move on to a super short unit called enthalpy, entropy, and Gibbs free energy. And we've already talked about enthalpy, entropy, and Gibbs free energy is what's going to be new, but we're going to tie this all in with things we've already done, so a lot of this will look familiar. The energy released or absorbed during a chemical reaction, the heat of reaction, is equal to the difference between the potential energy of the products and the potential energy of the reactants. So in a chemical reaction, reactants, and then we draw an arrow, go to products. We've done that for a long time now. So therefore, the change in potential energy is equal to the potential energy of the products minus the potential energy of the reactants. Potential energy can be thought of as heat energy, H, and we spent a whole unit on heat. So this will be a good refresher, bringing back this idea of heat. Therefore, delta H, kilojoules, is equal to the enthalpy of the products, the heat of the products, minus the heat of the reactants. And this is going to be our basic format for all of this very short unit, that we're going to take the energy values of the products and subtract the energy values of the reactants. This should be review, and this is great review to get ready for your final exam. When delta H is negative, and the heat is negative, the heat of the products is less than the heat of the reactants. But the big part is that this reaction is exothermic. And so if we look at this diagram, we haven't looked at a diagram like this before specifically, but we actually have. And when we looked at it, we had the whole reaction coordinate coming in here. So we had this as our activated complex, our activation energy, all in here, and then we're going to tie that all together in a minute. But what I want you to notice is that the heat of the products up here is greater than the heat of the reactants, and so this is our delta H. And so anytime our reaction is exothermic, this here, these reactants, will be higher than these products. And we really only looked at it in that sense, because we can also have a reaction that looks like this. When the delta H is positive, the enthalpy of the products is greater than the enthalpy of reactants, and the reaction is therefore endothermic. All these terms that we know already, we label that one as positive. And so here we have the same reaction coordinate that we have here. We still have our activation energy that would go all the way to here. We'd still have our activated complex, but notice our reactants are lower than our products. And so when the heat of our reactants here is less than the heat of our products, this delta H ends up being what we refer to as endothermic. So 90% of this is review, but just this idea of looking at where this heat comes in. Energy released or absorbed by a chemical reaction can be represented by a potential energy diagram, okay? And so here's these two reactions side by side. And so looking at it, it's the exact same reaction, but we're using here CH4 plus 2H2O as our reactants, going to CO2 plus 2H2O here. Or we're reversing that same reaction, and a reaction that's exothermic in one direction will be endothermic when it's in the other direction. This is all review. Activation energy is the minimum energy required to start a chemical reaction by providing colliding molecules with enough energy for effective collisions to occur. And the activated complex is the short-lived, unstable intermediate species located at the highest, look at the highest of the activation energy. So we have learned this graph already. We know this, and we've labeled it. What I want you to look at now is I want you to decide whether this graph here represents an exothermic or an endothermic reaction. Take a second and decide which one you think it is before I tell you the answer. Because my heat of reactants is greater than my heat of products, this is an exothermic reaction. And so we're drawing this as an exothermic reaction. And then this is also a review. A catalyst provides an alternate reaction pathway which has a lower activation energy than the uncatalyzed reaction. And so here is our catalyzed reaction. All of this we've already done, and this is all review. So take a look at table A6 in your packet. Notice the following things. The substances are in alphabetical order. It makes it easier to find. The enthalpy of formation, the delta H of formation, is in kilojoules per mole. Notice that the units are just written at the top of the chart and not on every single number to make the chart less cluttered. All free elements have an enthalpy of formation of 0. There are not compounds formed from the elements, so things that are just the elements in their standard states don't have an enthalpy of formation because the elements are at the lowest energy they can be at. We only have this enthalpy of formation when we form compounds. And still they're listed on the table as 0. And then the enthalpy of reaction is equal to the sum of the enthalpies of formation for the products minus the sum of the enthalpies of formation for the reactants. I know that sounds really confusing, but it's actually really, really simple. All of these fancy symbols here, this means the sum of, oh, and there should be a sum of sign in here. Sum of, and this is the change in enthalpy of the products minus the change in enthalpy of the reactants. And so you'll see when we go through a sample one that it's not terribly difficult. So here's our enthalpy calculations. We're going to look at a reaction. You have to be given a reaction, and in this case, these are really important because if you'll notice on your table, a lot of times we have other states, especially when it comes to water. Water can be gas, water can be a liquid, those sort of things. Here's our equation. The enthalpy of reactants is equal to the sum of the enthalpies of the products minus the sum of the enthalpies of the reactants. So we're going to look up our products. We only have one product, it's CO2. And so here is our problem. We have 2 moles. This 2 relates to this 2. And then this is the value off of the table. And so we're going to go 2 times the value that's associated with that number. And it's nice to put this in big square brackets to keep it organized. Minus the sum of the enthalpies of the reactants. And so here we have this 2 goes with this 2 times, and this is the value off the table, plus 1. Remember, we have an invisible 1 here, so there's our 1 and our 1. And then why is this 0? Well, it says it on the table, but also it's an element in its standard state. So it's an element in its standard state, so it doesn't have an enthalpy value. So we're going to do 2 times this number, and then 2 times this number, and subtract the 2. We don't need to do 1 times 0 in this case because it's going to be 0. So we end up with negative 787 kilojoules minus a minus 221. So it's 2 times 393, which is here, 2 times the 110, which is the 221. And we're going to actually end up adding that value. And this is the thing that you have to be careful of the most, is that we end up with a lot of this minus a minus. And we end up with a negative 565 kilojoules. Well, what does that tell us about the reaction? It tells us that the reaction is exothermic. And so this is a way that we can calculate and find the enthalpy of the reaction.